All right, let's get going on this. We have a little bit of calculator work, so if you want to grab your calculators and play along, that's fine. Anytime that you are able to use tabular, I encourage you to do that. So anytime we have a polynomial and then the other function is something that we can take the antiderivative of, go ahead and use tabular. So 6, 0, that's the derivative. Here's the antiderivative, and negative cosine of x. Then we have the diagonals and plus minus. So 6x sine of x plus 6 cosine of x. Plus c is the antiderivative. Here we have the derivative of the integral. So that's t to the 6th square root minus 4, but then times the derivative of that right there. 3 is the formal definition of derivative. So this is secant squared of x. Then the last one, AP really likes this question. We're going to let x equal, not u, but 4u. So dx is equal to 4 du. So dx becomes 4 du. And then we have this 5 that we can pull out. And that's 1 over 16u squared plus 16. When we let x equal 4u. So that's 20 over 16 integral of 1 over u squared plus 1 du. And so 5/4 inverse tangent of x over 4 plus c. Because u is x over 4. You got to divide by 4. Today we're going to talk about logistic growth. So now consider the case of a population P with a growth curve as a function of time that begins increasing and concave up, then turns increasing and concave down as it approaches the carrying capacity of the habitat. What does all that mean? So we have a logistic curve right here. This isn't the growth, this is the actual population. But if you start with a population, the population will grow exponentially, but eventually exponential growth becomes ridiculous. Exponential growth says if I put 50 fish into that pond, eventually there's going to be 5 billion fish. Just piles of fish coming out of the water. Well, you know that that's ridiculous, that that's not the case. That pond over time will have a carrying capacity. Eventually, there'll be so many fish in there, if the conditions are good enough, that the fish will run out of room, run out of food, run out of space. It'll reach its limit. So more realistic growth is growing exponentially, but then just kind of leveling off and eventually getting to a horizontal asymptote that is called the carrying capacity. How many fish can actually live in that pond? Well, how are we going to get this limiting factor? How are we going to limit it to 10,000 fish? Or how are we going to limit it to 500 bears in the forest? Well, if we take the maximum the habitat can handle and minus its population and multiply, let's say an exponential growth, we multiply it times this limiting factor. If the population of bears could be 100, as we get to, let's say, 90, we're going to multiply this by 10. When we get to 95 bears, we're going to multiply this now, not times 10, but times 5. And eventually, when we know we have 100 bears, we're going to say that the growth is 0. Because eventually, we'll multiply by 0 once we get to that point, once we get to that carrying capacity. So this is a logistic differential equation right there. That limits our population. And that's way more realistic. All right, let's do some math. The growth rate of a population P of bears in a newly established wildlife preserve is modeled by the differential equation, where T is measured in years. What is the carrying capacity for bears in the wildlife preserve? 100. 100 bears. What is the bear population when the population is growing the fastest? In other words, when do we have a lot of bears but a lot of room left and a lot of food and a lot of caves for them to hibernate? When will there be a lot of bears but still a lot of room, a lot of resources left? Halfway, yeah. Halfway. You'll have a lot of bears and a lot of room left. After that, you're going to start running out of room, running out of food. Where are they going to hibernate? It becomes a little bit more scarce. So the population will flourish when you're at half the carrying capacity. As you get past that, the rate's going to start to slow down. What is the rate of change of the population when it is growing the fastest? We know it's 50, all right, but what is that rate? That's the question. So we have 0.008 times 50 times 100 minus 50, which ends up being 50 times 50. So 0.008 times 50 squared, let's say. So 20 bears per year. So that's when the bears are flourishing the most. You'll see an increase of around 20 per year. Letter D, what is the fastest rate of growth if we start with 20 bears? Well, if we start with 20 bears, the fastest growth will be when the population is 50. So this answer is exactly the same. Letter E says, what is the fastest rate of growth if you introduce more than half the carrying capacity? What if you introduce more than 60? Well, your population is going to immediately slow down. I'm not saying it's going to be zero. I'm going to say it's immediately going to slow down because you're past halfway already at the very beginning. So the maximum rate at which the bears will grow is right away. That's the fastest it'll grow because after this, it's already slowing down. We know that because we're already past halfway. So 0.008 times 60 times 40. So we're already down to 19.2 bears per year. And since we're already past halfway, it's not going to get any faster. It will only get slower from there. Because our multiplier is going to start to get smaller and smaller and smaller. Any questions on that concept there? So if you're before halfway, you use halfway. If you're after halfway, you use the current value. In 1985 and 1987, the Michigan Department of Natural Resources airlifted 61 moose from Algonquin Park, Ontario to Marquette County in the Upper Peninsula. It was originally hoped that the population P would reach carrying capacity in about 25 years with a growth rate of that, logistic. Hey, according to the model, what is the carrying capacity? Well, 1,000 meese. What is the largest rate of growth if P of 0 equals 20? Well, that's not past halfway. So the largest rate we're going to see is when we're at half of the population, half of the carrying capacity. So that'll be 500 times, it ends up being 1,000 minus 500. So 0.003 times 500 squared. So 750. 750, what is this? Moose per year. Letter C, what is the largest rate of growth if we're already past the halfway point? Well, the fastest growth we're going to see is right away. Times what, 400? And we can see that's already, oh, wait a minute. Was the other one 750? No. Oh, I missed a 0. I thought that was kind of high. Yeah, 75, not 750, because this should be smaller. 72 moose per year. Solve the differential equation with the initial condition of P of 0 is 61. This is a long process. I think I asked you in the homework to do this either once or twice. And so when I collect homework tomorrow, when I look at it, I want to see this process. However, it's a long process. It's really not necessary as far as the test is concerned to know this process. We need to know the result of it. So I don't want you spending a half hour studying this for the test. That wouldn't be fair, because we're not going to use it on the test. I still want you to do it. So for the homework, we're going to do it. Then after that, you just have to know the result. Now this is long. I'm not being sarcastic or funny or anything. So you might want to start off to the right, like over here, because there's a lot of steps. No step is particularly hard, but it's just a long process to solve the differential equation. And I probably should have put using partial fractions. So if it says use partial fractions in your homework, that's what I expect. If it doesn't, you can just use the formula that we'll end up having. All right, anyway, here we go, D. We want to solve the differential equation. We have 1 over P times 1,000 minus P. dP is equal to 0.0003 dt. So we split the differentials, split the variables. P with dP, T's with T's. We're going to integrate, but we have to integrate using partial fractions. So we're going to put A over P and B over 1,000 minus P. And they need each other's denominator. So 1 is equal to A times 1,000 minus P, and B needs the P. We're going to let P equal 1,000. So we get 1 is equal to 1,000 B. So B is 1 over 1,000. We're going to let P equal 0. And so that makes 1 equal A times 1,000 when we put 0 in. So A is also 1 over 1,000. So there's the partial fraction part. And that's the only way we can do the antiderivative of the left side, is with partial fractions. So this left side becomes 1 over 1,000 over P plus 1 over 1,000 over 1,000 minus P dP. Let's not integrate this yet. We could, but I don't want to. Well, now what we could do is factor out 1 over 1,000 here, and we could pull out the 0.003, and we could multiply everything by 1,000. And when you do that, you cancel out this fraction. So this is 1 over P plus 1 over 1,000 minus P dP is equal to, if I multiply this times 1,000, it's 0.3. Because multiplying by 1,000 moves that decimal point over 3 places. Well, now we can do the antiderivative. So we're going to go natural log absolute value of P plus natural log absolute value of 1,000 minus P is equal to 0.3 T plus C. Well, I know where we're headed with this. There's a little trick here that is not obvious. I need, that's a minus, because the derivative of the inside would be negative. I almost missed that. I caught it though. It's easy for me to miss too, quite frankly. All right, so I need the 1,000 minus P to be on the top, not on the bottom. And it helps to know where you're going with this. So we're going to run a negative through all this. So natural log absolute value of 1,000 minus P minus natural log of P is equal to negative 0.3T plus C. And you don't have to write minus C. C absorbs about everything. You can change it pretty much to anything you want. And I'll explain that here in a second. Well, now using the power rule, or no, the rules for natural log, this can be 1,000 minus P over P. And I wanted that to be on the top. And I wanted that to be on the top because now I can use common denominator. So 1,000 over P minus P over P, which is 1, is equal to e to the negative 0.3t plus c. So we take it to exponential and use common denominator. Well, now we can add the 1 over. So 1,000 over P is equal to 1 plus, how about we do this? E to the C times e to the negative 0.3t. Because we can split those powers using multiplication. Because when you multiply them together, you would add the powers. Well, now we can divide by this and multiply by this. So P is equal to 1,000 over 1 plus, instead of e to the c, I just want c. And you're like, oh, wait a minute. Oh, whoa, whoa, whoa. Okay, you're like, I'll buy the fact that I don't need to multiply by a negative, maybe. But I can just take e to the c and just change it to c. How in the world can I make that leap? And here's what I'll tell you. We're going to plug in 61 in here. We're going to plug e to the 0 here, and that'll just be 1. So if we multiply by 1 plus c and divide by 61, c ends up being 1,000 divided by 61 minus 1. So c ends up being, minus 1. Well, it's 15. 15.393. If I would have left it as e to the c, I would just, if I want to know, well, what c makes this 15.393? And it's the natural log of that. So the natural log of this answer is that. So if I would have left it as e to the c, my c would be this. If I just change it to c, it's this value right here, which gets you to the same place. It would get you to the same value. So if you leave it as e to the c, you're going to get a different c, but in the end, 15 point something is going to be sitting in that spot no matter what. Doesn't matter what I have c as. So that's why you can change c to pretty much anything you want. All right, anyway, we got to finish this off. We found the c, so we want this right here. That's what we're after. It's like, what are we even trying to do? We're trying to find this equation. 1 plus 15.393 e to the negative 0.3t. That's the final equation. That's the equation for the population given the differential equation. So we backed up and did antiderivative, but it's a very long process. Now, if you look on the next chart, it says something to this effect. P is equal to the maximum capacity, 1 plus A, e to the negative mkt. So in other words, how did I get, they don't write C, they write A, and that 0.1, excuse me, it's 0.1 later. 0.3 right here is the result of taking this m times the constant. So if you take that times that, that's what gives you the coefficient up in that exponent. So it's m times k, and then t is the variable. If we have you use this on the test, it'll be on the test. You are not expected to memorize it. If you use it a few times in your homework, you probably will have it memorized, though. All right, anyway, there's the chart that says if you have this differential equation, this is the equation that you'd get if you solved it. The logistic equation describes the growth of a population P where T is measured in years. In each case, find A, the carrying capacity of the population. So 24 would be 700. That's A. B, the size of the population when it is growing the fastest, 350. And C, the rate at which the population is growing when it is growing the fastest. So that's going to be 0.0008 times 350 squared. So the rate at its fastest will be 98. That's when the population has reached half the carrying capacity. We already did that. We got better things to do. I'm going to take that one off. But if it says use partial fractions in the homework, you got to do that once or twice. I'm not going to assign 10 of those. A certain wild animal preserve can support no more than 250 lowland gorillas. 28 gorillas were known to be in the preserve in 1970. Assume that the rate of growth of the population is modeled by that function right there. So this is P of T, not the rate, but that's the actual population. What is the greatest rate of growth if P of 0 is equal to 28? So if we introduce 28 gorillas into the population, the fastest rate will be when the population is 125. So times 125, and then times 125, because that'll be the halfway point. So 0.0004 times 125 squared. So 6.25 gorillas per year. B, what is the greatest rate of growth if we've already introduced more than half the carrying capacity? Well, the maximum growth is going to be right away, because after this, the growth is just going to start slowing down. So the growth will start slowing immediately. So 250 minus 200. 0.0004 times 250 times 50. So it's already decreasing, 5 gorillas per year. So if you introduce less than half into the habitat, use half. If you're over half, that's the value you have to start with. Letter C says find a formula for the gorilla population in terms of T. Doesn't say use partial fractions. So the population is 250 over 1 plus A e to the, I need M times K. 0.0004 times 250. So that coefficient, there's that 0.1 that I was thinking about. There's almost the formula, almost. But we need A. To get A, we're going to use the fact that there's 28 on year 0. We're saying 1970 is year 0. So P is equal to 250. Whoops, not P, excuse me, 28. $250 over 1 plus A. E to the 0 is 1. So times 1. So these two trade places. So A is equal to, we need 250 divided by 28, and then minus 1 from that. 7.928. So P is equal to 250 over 1 plus 7.928 e to the negative 0.1 t. D, how long will it take for the gorilla population to reach the carrying capacity of the preserve? There's a little trick to this. So what we're saying is, statistically, if you have 249.5, that's 250, because we'll round up. So if you set this to 250, that will, in theory, that will never happen because it's an asymptote. That maximum carry capacity is an asymptote, so the curve will never get to it. So the question is, or the answer is kind of never if we didn't use something that would be statistically accurate. And we're going to say for letter D that all we need is 249.5. 28. Well, that T is really buried, so we got to get it out of there. So let's multiply by the denominator and divide by 249.5. So these two trade places. So I need 250 divided by 249.5. So 250 divided by 249.5 minus 1 from that. Divide by 7.928. And here's where we're sitting. E to the negative 0.1 t is equal to this 0.00025, keep on going. So we'll take the natural log of that answer, and then I would have to divide by negative 0.1. So about 82 years. 82.83 years is when we're at 249.5, and statistically we would round that up to 250. If you put 250 in there, you can't do the problem. You'll end up taking the natural log of 0 if you try to put 250 in there. I would like to erase this. I'm kind of running out of room. Everybody okay if I erase this? You have plenty of white space up above because we didn't use that problem. We didn't do that problem. So we got a couple left, and that's it. But we do need a little bit of room for this. Everybody good? All right. For letter E, it says if P of 0 is 28, use Euler's method to approximate P of 10 using two equal steps. So we're saying we got the point 0.28, then we'd have 5 comma something, and then 10 comma something. So we're going to use Euler's method twice. Well, I got to get from 0 to 10 with 2 steps. We know the change in T. This is time, that's the population. We changed T by 5. We added 5 every time. Well, now what should we add to P? So dP is equal to 0.0004 P times 250 minus P, and then all of that times dt. Because I'm multiplying dt over. Well, dt is multiplied times that entire side. So our change in P is 0.0004 times 28 times 250 minus 28 times 5. 4 times 28 times 250 minus 28, and then times 5. So that's the change in P. So we got to add that to 28. So we're at 40.432. Well, we got to do that one more time. So dP is 0.0004 times 40.432 times 250 minus 40.432 times 5. Got that, times 250 minus 40.432. I think I have an extra parenthesis. Yep. Dang it. Delete that. Boom. Times 5. But then I got to add that to 40.432 because that's the change. It changes by 16. Oh, I missed the plus. Plus 40.432. 57. So 57.378. That's our answer, but then letter F says And this is why I gave you the graph. Otherwise, we didn't use the graph at all. It says, is the approximation in letter E an underestimate or an overestimate? Well, we went from 0 to 10. So we went from here to here. Now that's concave up. So if I'm going to use tangent lines to make an approximation, it's actually here, and then a tangent line here, and that's where we're sitting right there. Well, because this is concave up, all the tangent lines will lie below. So this is an underestimate. Why? Graph of P is concave up from t equals 0 to t equals 10. That causes an underestimate. Now, if you're on the part of the graph where it's now concave down and you use tangent lines, all your tangent lines will be above the graph, so that'll be an overestimate.